Hello, everyone. My name is Prateek Mittal. I'm a professor at Princeton University. And today I'm delighted to be talking about a new approach for protecting legacy internet communications using a secure backbone. This is joint work with outstanding collaborators across Princeton University, University of Virginia, as well as ETH Zurich. I'll begin by highlighting the insecurity in internet routing today, since the border gateway protocol is vulnerable to routing attacks. These routing attacks can have critical consequences for internet applications, including the security of TLS encryption, including the anonymity of networks like Tor, including the security of cryptocurrencies such as Bitcoin. To appreciate the devastating impact that routing attacks can have on these applications, let us consider the motivating example of domain validation protocol for TLS certificates. The domain validation protocol allows the owner of the domain, such as example.com, to prove to certificate authorities on the internet, such as Let's Encrypt, using a challenge response protocol, that they're indeed the owner of a particular domain. This can be done, for example, by Let's Encrypt issuing a verification challenge to the owner, asking it to make custom modifications to the example.com web server. Once those modifications have been made, Let's Encrypt could validate those modifications via a simple HTTP GET request, for example, to the URL example.com verify.html. And upon receiving a valid HTTP response, Let's Encrypt could issue a valid digital certificate to the owner of example.com. However, in our research at Princeton that was published at USENIX Security in 2018, we empirically demonstrated how routing attacks can compromise this domain validation protocol. A key insight is that in steps 5 and 6, the HTTP GET request as well as the HTTP response message are not encrypted. And this is, in fact, very fundamental to the domain validation protocol, because this protocol helps bootstrap encryption on the internet. So it's very ironical that this protocol itself cannot rely on encryption. And as a result, an adversary can launch BGP hijack attacks to intercept HTTP verification requests and thereby spoof HTTP responses. An attacker can thus obtain valid digital certificates, and thus the very foundations of protocols like HTTPS and TLS are vulnerable to attack. In response to the threat of such routing attacks and the impact that they can have on critical applications, a number of secure routing protocols have been proposed. An exciting development has been the SCiON protocol in its real-world deployment, because it has a cryptographically secure control plane that fundamentally eliminates the threat of routing attacks. Now, all autonomous systems that participate in the SCiON protocol can now offer enhanced reliability and enhanced security to their customers. However, observe that these benefits are limited to those entities that directly participate in the network of SCiON-enabled ISPs. Unfortunately, the deployment of the SCiON backbone is still limited. And as a result, there are a number of legacy clients on the internet that are unable to benefit from the enhanced security and reliability properties of the SCiON protocol. And this is the key question that motivates our joint research. How can we extend the security benefits of even limited SCiON deployment to the broader internet? A key insight in our work is the introduction of a new entity called the SCiON Backbone AS, or the SBAS, that helps serve as a bridge between the legacy internet and the SCiON network. SBAS can optimize regular internet traffic using the SCiON backbone for security, including defense against prefix hijack attacks, for example. While security was the original motivation for our work, we later realized that the same approach can also help optimize for the latency that's experienced by legacy clients. And it can also help drive down carbon emissions in the process of internet routing. Interestingly, this approach is completely transparent to internet hosts who do not have to be upgraded either at the client end or at the source end. And thus, this architecture represents a promising approach to attract traffic onto the SCiON network. Now, let's see how the SBAS approach can help bridge the gap between the legacy internet and the SCiON world. Now, an existing SCiON network can be augmented to create the SBAS. Some ASs that want to offer this bridge can serve as a point of presence, abbreviated as a POP, and create a secure mesh topology amongst themselves using the IBGP protocol. The secure mesh topology is really helpful for these points of presence to coordinate amongst themselves and exchange BGP information. Towards the outside world, this SBAS behaves as a single autonomous system and advertises BGP routes to the legacy environment. Finally, customers who are seeking to improve their routing security can benefit from SBAS even when they don't have a SCiON connection. And for this purpose, the points of presence provide a VPN endpoint that allows enterprise networks or servers to connect securely to the SCiON network and have their prefixes redistributed by the SBAS to the broader BGP ecosystem. Now, let's see how this approach can provide end-to-end security benefits between a sender and a receiver. Let's consider an example of an autonomous system A on the left-hand side of this slide, signing up at its local ISP for SBAS, and then it starts to make BGP announcements. The announcement is carried over a VPN tunnel that connects to ideally a close point of presence that's part of the SBAS architecture. The point of presence uses the secure IBGP mesh topology to relay this BGP announcements to all of the other points of presence. And these points of presence then further propagate this announcement to the rest of the BGP speaking ecosystem using the SBAS AS number. We emphasize that this approach is fully compatible with standard BGP operations today and still allow the customer to make announcements for the same prefix to the legacy internet as well. Now, crucially, other legacy clients that now want to connect to a server that's located in autonomous system A do not even need to be aware of either the SBAS architecture or the SCiON protocol to benefit from this routing announcement. Due to the properties of the shortest path selection in the BGP protocol, their traffic is likely going to be attracted by the SBAS, in this case, the point of presence that's closest to the legacy client on the bottom right part of this of the slide. Once it reaches the closest point of presence, it will be encapsulated over the SCiON network until it reaches the point of presence on the left-hand side of the slide, which is closest to autonomous system number A, which can then transmit this message forward. Now, this approach helps enhance the end-to-end resilience of the system against prefix hijack attacks, because communications between the 2 points of presence are fundamentally secure using the cryptographic properties of the SCiON protocol, while communications between the points of presence and either the sender and the receiver of the communications are secure because of the shortest path routing properties of BGP, which makes it much more likely that these senders and receivers connect to SBAS as opposed to being misled by longer malicious BGP announcements made by an adversary. Thus, SBAS achieves improved hijack resilience for customer prefixes. We empirically demonstrated this benefit of the SBAS protocol, both using real-world test announcements using the peering framework, as well as internet-scale simulations that we performed as part of our research. So we are demonstrating two graphs here on the slide on the right-hand side that show the CDF of the end-to-end resilience experienced by our SBAS system. You can interpret the notion of resilience as the probability that a client-to-server connection is immune against malicious routing attacks. And we can see that an SBAS deployment with only a handful of nodes still provides significant improvement over the baseline scenario of not having an SBAS at all. The bottom graph shows the combined benefits of our SBAS approach with a strategy where all ASs are universally enforcing route origin validation. And we can see that route origin validation has complementary synergies to SBAS, and the combination of ROV with SBAS can offer even improved resilience values, which demonstrates the promise of our protocol. Now, because the SBAS requires close coordination across different points of presence, it does require a governance structure. So, for example, the points of presence collectively own an autonomous system number that they use to make BGP announcements. And they also need to coordinate customer relationships since they are re-announcing each other's customer prefixes. So to enable this coordination, we offer a range of possibilities. The first of which could be a federation of providers, very similar to the Manners project in the BGP speaking world. A second possibility could be that of a multi-stakeholder organization, such as the SCiON Foundation. A third possibility could be that of regional internet registries, similar to the RIPE NCC, while a fourth possibility could be that of a decentralized governance model, very similar to the Tor project. We look forward to hearing your inputs about what might be an ideal governance model for the SBAS initiative. To conclude, our proposal for a secure backbone AS offers a bridge between the legacy internet and the SCiON network. It has the attractive property of enhancing the amount of traffic that goes over the SCiON network, which will then provide financial benefits to SCiON-enabled ISPs. These benefits could come from providing services to customers that are interested in receiving hijack resilient routing properties, perhaps enterprise customers, for example. These could be customers that are interested in improved carbon efficiency of their routing in a move towards a greener internet. Or these could be customers that are interested in receiving latency optimized services in a move towards a gaming-oriented internet. And our proposed SBAS architecture can simultaneously achieve all of these benefits. So this brings me to a conclusion of my talk, and we look forward to hearing any comments that you might have about our protocol. And we'd be particularly interested to see if your entity might be interested in partnering with us on a real-world deployment of the SBAS protocol. Thank you.
So Professor Prateek Mittal, again, is in New Jersey, and it's 4 a.m. there. So here to answer some questions is Professor Parrig. We have our first one. How can SBAS enable the use of SCiON for standard internet applications, Professor Parrig?
Right. So to also reflect on the previous 3 talks, we're trying this year to get more and more traffic onto the SCiON network and enable the SCiON benefits to provide advantages for regular internet communication. And so all these talks you've seen about also green routing, as well as François' bootstrapping system and this SBAS system all contribute to enabling the wide use of SCiON. So in particular, in SBAS, and if you remember this diagram I showed in the early presentation, almost nothing needs to change, right? So one single entity needs to opt in, we call this, and then so either the sender or the receiver, as long as they opt in, the communication will then go over the SCiON network if SCiON can actually improve it. If not, it will just go on the standard internet. And so, for instance, ways to then use this system is to say we optimize for security, which is what Prateek talked about. And this is how the system actually came out to be, because Prateek worked and his team attacked all the CAs worldwide. They were able to, with their system, forge attacks and forge certificates for any website in the world, making use of BGP-based attacks or DNS-based attacks. So that famous result, then they helped improve the security using multi-vantage point verification, which Prateek's team suggested, and that was built into the Let's Encrypt system. Now, knowing about SCiON, and we started collaborating of how can we much further improve the security of this Let's Encrypt domain validation. And so these ideas from SBAS came up. And so this is one way also to enhance security of today's internet applications without making any changes to the end hosts, except one side has to opt in and has to be part. So one of the IP prefixes, either sender or the receiver, needs to be part of this SBAS prefix base that SBAS announces to BGP, as Prateek was showing. And then both sides, sender to receiver and receiver back to sender, will most likely go over this SBAS and SCiON backbone. And so the question was, well, how can we enhance today's internet applications if we have, for instance, an entity who wants to optimize for CO2, let's say, a private person, an ISP can offer a service and say, we can offer your internet communications CO2 footprint. And then the ISP uses this SBAS system to then optimize the CO2 for the communication with any destination in the world, right? So the beauty of the system is that both the packet from the user to the ISP and then in the SCiON network is then CO2 optimized, but also the response, because the prefix IP address range would be announced by SBAS. So the response packet, as Prateek was showing, would then also again come back via the same system, even though the receiver is somewhere around at the other end of the world, has no ISP that supports SCiON and has no notion of SCiON. It's really a normal connection. And so we find this is really exciting. And so not only CO2 are possible or security, but also latency. So for gaming users, we can have an optimization for latency so that the latency is minimized. And this would work for arbitrary entities, and this can be a good way to enhance current internet applications.
There are many more questions, Professor Perig, but I think we only have time for one more. How do you solve the inherent scalability limitation of iBGP, more so the full mesh iBGP?
Right. That's a very good question, I think, here from the room. BGP has inherent limitations, and obviously there are existing techniques to try to deal with that. If it comes to that, it means also it's a sign of success if we run into these limitations, if this SBAS system gets large enough. And hopefully at some point also the deployment will switch over to more SCiON-based end applications that then can natively make use of SCiON. So SBAS essentially is a way to bridge the gap and provide the advantages now to applications, and we believe as the system grows, eventually it will switch over to what François was presenting, so that end hosts that are SCiON-enabled, if they're near an entity, or if they're in an ISP that has SCiON support, automatically they'll get configured and automatically they can make use of SCiON. So we're looking at all the educational ISPs offering SCiON, and if we can set up the system François was presenting, then all the users at all these universities that are connected via these networks will automatically have native SCiON connectivity if their applications can support SCiON. And so we hope that we can reach perhaps up to 10 million users with SCiON and Internet 2 and Switch and Koreanet, which is a Korean research network that we're collaborating with. And so we're looking at also getting native SCiON code directly into applications. And as a result, when people download a new version of the application, it may be able to automatically pick up the fact that it's near or in a AS that has SCiON support, and then natively start using SCiON. And we think this is a really exciting way to also bootstrap the whole usage of SCiON. And so it may very well be that people here download a new version of some application that has this built in, and they may be starting to use SCiON even this year without knowing. Hopefully you'll see things work better. And so that's a way we believe we can bootstrap the whole ecosystem in a faster way. Right? So,
I
other
suppose
questions?
we have time for, we can squeeze one more question in. Would it be possible to misuse this noble intention to control or even exclude parts of the internet, such as countries or other parties? Right.
Government censorship is an important point that often comes up. We've seen, though, that in today's internet, censorship already works quite well. What also works is even remote censorship, where one government entity, through an internet kill switch, can take down the internet at other parts of the world. And so SCiON doesn't make this any worse, as it already is. It actually makes things better. SCiON introduces transparency and higher levels of security that many of the ways that in which repressive governments use today to perform censorship become impossible in SCiON because of the routing security, for instance, is one example of ways of applying censorship that will not be possible anymore in SCiON. I mean, fundamentally speaking, if you have a country that is connected with over connections that the government controls to the rest of the internet, that entity can always cut these lines, and there's no technology that can do any better and can prevent this. But SCiON can prevent many aspects of censorship, and having had many discussions over the past years with people living in these countries being confronted with these issues, the conclusion always was SCiON will actually improve the situation for citizens and will enable more security for everyone and make attacks more transparent as well if they do occur. Right.
Great. Thank you, Professor Perig, and thank you to Professor Mittal. Up next, we're going to connect to London.